Today we're going to go over some more examples using the laws of logarithms to try to point out. I'm going to try to point out some areas where you could make an error. Now we have to be careful with division. When we are dividing, when we are separating our arguments out from division, you've got to remember that the entire denominator is negated. So when you separate them out, you either have to use parentheses or you have to remember to distribute the negative when you break apart this product that's in the denominator. So to get started, we have log to the base 3, and then my argument is 3a over b, and this is the cube root of c. So I'm going to start to break this apart by separating out the numerator and denominator with subtraction. And here's what that looks like. I end up with log to the base 3 of 3a minus log to the base 3 of b, and then instead of writing the cube root, I write c to the 1/3. I want to write it as an exponent so I can use that third law to break that apart. So here's where you have to be careful. This entire thing needs to be negated when I break it apart. So you either put parentheses here or a subtraction sign in front of each logarithm when you separate them. Separating out the first guy, this is a product, 3 times a, so I can use addition, log to the base 3 of 3 plus log to the base 3 of a minus, and then over here in parentheses, log to the base 3 of b plus log to the base 3 of c to the 1/3. It's totally okay to leave it like that. I have addition here because the entire thing is in parentheses. If I didn't have these brackets, actually I call them parentheses, they're brackets, whatever, then this subtraction would have to be distributed. So I'm going to do one more step, and I'm going to cover two things. I'm going to bring this exponent down in front. That's the third law. Everything else is separated out except for log to the base 3 of 3. And yes, that is my dog barking. You'll have to ignore him. Log to the base 3 of 3. This is one of the properties that we have. And this simplifies to 1. So it's 1 plus log to the base 3 of a minus log to the base 3 of b plus 1/3 log to the base 3 of c. You can leave your answer like that, or if you wanted to eliminate the parentheses, you would distribute the negative, and the first term would be negative, and so would the second term. So here's an example where we're going the other way. We're going to take these three terms and we're going to write as a single logarithm. Now we have to be careful. Again, I'm trying to point out the areas where you're going to make a mistake if you're not careful. If you look at the sign of the coefficient, this guy's positive, this guy's negative, this guy's positive. Any logarithm with a negative coefficient is going to end up in the denominator. The argument will be in the denominator when you're done. And kids argue with me about that. And you got to understand, if I use the commutative property, I could rearrange these terms so the minus 3 is at the end. And then you could see that, yes, in fact, the anything negative, the minus 3, is going to be in the denominator. So let me just start off. We're going to start by using the third law and bring our exponent up, bring our exponent up, bring our exponent up. So I have log to the base 2 of x to the 1/2 minus log to the base 2 of y cubed plus log to the base 2 of z squared. Now all I need to do is combine them. So again, when I look at this, the x to the 1/2 and the z squared are going to be in the numerator. The y cubed is in the denominator. A lot of times kids will join these first, and then you'll put the z squared in the denominator. Don't do that. It depends on the sign in front of the logarithm. I'll show you because I'm going to rearrange these terms first. And instead of the 1/2, I'm going to use the square root of x. And plus log to the base 2 of z squared minus log to the base 2 of y cubed. I didn't change anything. All I did was rearrange the terms with the commutative property, or commutative property. That's fine. But now you can see that the only thing in the denominator is going to be the y cubed. So I can write this as a single logarithm, log to the base 2 of the square root of x times z squared all over y cubed. So let's do this again. I'm going to write as a single logarithm. We have a base 10, the common log, and I have three terms again. And once again, the middle term is negative, so this is the only guy that's going to be in the denominator. He's positive, so when I finish with these guys, they're going to be in the numerator. Taking this one step at a time, I bring the exponents up, log to x to the fourth minus log of, I'm going to write this as a cube root, the cube root of x squared plus 1 plus the log of x minus 1 squared. Now I just bring everything in. This argument is going to be in the denominator, this one's going to be in the numerator, and this one's going to be in the numerator. And please remember, when we bring these things together, we write as a single logarithm. Only the arguments are going to be brought together. Okay, so it's not log of x to the fourth divided by log of the cube root of that stuff. No, we have a single logarithm. And in here, in the numerator, is x to the fourth and x minus 1 quantity squared. And then the one with the negative coefficient is going to be the cube root of x squared plus 1. And that's it for that one. I'm going to go through the process of deriving the change of base formula. Now, change of base is getting less and less necessary with the newer calculators, because I think that the newer calculators you can actually enter in whatever base you want. But if you have an older calculator, this is good to know, especially when you're trying to graph a log function. So we're going to start off, we're going to let y be equal to log to the base b of x. So I have a base b that's not in our calculator, and we want to make it so that we can put it in one of our old-fashioned calculators. Rewriting this as an exponent, we have b raised to an exponent of y is equal to x. I'm going to use that, and I'm going to take, let's say, the log of something else of both sides. So usually that would be the common log or the natural log, but it can be anything. Log to the base a of b to the y is equal to log to the base a of x. Then I'm going to use my third law, and I'm going to bring this y down in front. So I have y times log to the base a of b is equal to log to the base a of x, and then finally I have the change of base formula. If I have y is equal to log to the base a of x over log to the base a of b. Well, the original value of y was up here, log the base b of x. So on the next page I'm going to write the change of base formula, but this is how we get it. So our change of base formula looks like this. The log of any base can be rewritten into log to the base a of the argument over log to the base a of the other base. This lets us use natural log or common log or whatever is in your calculator as a change of base. So I could say, for example, if I want to evaluate log to the base 3 of 5, in most calculators you can't just enter that in. Well, that's the same as the common log of 5 over the common log of 3. So it's a handy little tool to use, especially if you're going to start graphing functions where your graphing calculator doesn't recognize logs of different bases, only the common log and the natural log. So just to finish this, to show you that it doesn't matter whether you use common log or natural log, you can evaluate let's say log to the base 8 of 5, whoop, that's funny looking 8, log to the base 8 of 5 by writing the natural log of 5 over the natural log, I can't even write natural log today, natural log of 5 over the natural log of 8, and that's going to be the same thing as the common log of 5 over the common log of 8. In either case, you'll get some number like approximately 0.7740. You can check it out yourself with your calculator. It doesn't matter whether you use common log or natural log. The change of base is applicable to either one. So what we'll do in class is practice a lot more of these things, expanding and compressing these logarithmic expressions using the laws of logarithms.